Hello, and welcome to an introduction to a new concept for Kubernetes called vessels. The problem: how do I manage my complex application on Kubernetes? To really get into this, let's define a complex application. A complex application is an application that is not cloud native, often made up of multiple containers that can be both stateful and stateless. So if you think about an application that's like this, it's often the case they have multiple services that depend or even expect something from one another at a certain point in time. Where this really shows itself as a problem is with operations like deploy, reconfigure, scale, upgrade, or even restart. These operations for a complex application often require a set of sequential steps so that the services in the complex application will be able to reach a healthy state. The problem with this in Kubernetes is that Kubernetes does not have the tools to fill this need. And the reason it doesn't is because Kubernetes expects all applications it manages to be cloud native. And so how do we really bridge that gap? Well, so one way to look at this is we need to make our complex application seem cloud native. If we do that, we'll be able to leverage all the features in Kubernetes, and then on top of that, provide any sort of the workflows in between Kubernetes and the application in order to really make it function all the time, so that those operations like deploy, upgrade, scale, restart will function the same way a regular cloud native application would. So let's get into the vessel. The vessel is a Kubernetes third-party resource and pod that enable lifecycle management for complex applications. There's two pieces, the third-party resource and the pod. I'll get into next in the diagram. Beginning the top side of this diagram, we have our complex application. We have three pods. In this case, we show one of the services in the complex application dying and restarting. When it respawns, the vessel will start first. Inside the vessel, we have our controller and we have a set of workflows. The controller is going to look at the status of the cluster and determine a workflow it needs to run. The second part of this is the third-party resource. The third-party resource is a template created by the user that is going to reflect the user opinion in a certain point in time. When it's created, it is added as a Kubernetes REST API endpoint so that it can be queried by the vessel. When the vessel is started and selects a workflow, it's going to ask the third-party resource some questions to determine how it should run. So for example, these questions are workflow type. In this case, I selected Ansible. This could be anything. It could be a whole number of workflows. The controller only expects some workflow to handle the problem on the back end. The second question, allowed to run this workflow. This is a very important question because the user is not always present at the time an application event occurs. And so what's important here is that we always reflect the user's opinion at any point in time through a single source of truth, and in this case, the third-party resource will reflect that. So in the case that the user does not want this workflow to run, you could select no. And the reason that could be the case is because this workflow could be a very sensitive series of steps that the user wants to handle so that it is clear that the application returns to health without any worry. But in the case that the user trusts the application to return to health, you can select this so it happens automatically. If it's allowed to run, you follow the arrow and we will run the workflow that will bring the complex application back to health. Next, I'll show a demonstration of this demonstration for today for a complex application running on Kubernetes is going to be a multi-master MariaDB cluster. The reason I'm using a multi-master MariaDB cluster is because it represents a complex application where there are multiple services that depend and interact with one another and have state. What's important here with a multi-master cluster is what I want to show by showing the physical volumes that exist in Kubernetes. Each MariaDB instance has its own physical volume. So instead of using a shared storage between a bunch of instances, I'm actually having each of the masters, have their own set of storage. What's significant about this is that any interaction with the database is going to be replicated synchronously across all the nodes. The scenario that I want to demonstrate that really shows the importance of vessels when you're dealing with a complex application involves destroying the cluster. To destroy the cluster, what I'm going to do is I'm going to kill all the nodes at the same time. And when I do that, what's going to happen is all three of these are going to be restarted by Kubernetes. Normally, in a situation of a cloud-native application, the restart wouldn't be a problem. But in this scenario, if I destroy all three of these at the same time, and right before I do so, I change the sequence number of one of the three masters of my cluster, I can run into a situation where I'll have data in one of the three masters that will not be replicated across the cluster. This is very important and a very sensitive state where operators really can run into because of some sort of power outage that causes their nodes to disappear when there were transactions occurring and replication never completed. So in the case of the restart, we do not want to restart all three nodes at the same time. We want them to start in order. We need to pick which database is the latest and bootstrap from that database to start the cluster, and then have the remaining instances join the cluster. Otherwise, if you restart, you're going to have a 1 in 3 chance of actually maintaining your data. Otherwise, you're going to lose some. So I'm going to demonstrate that here. We're going to kill all three of those instances, and you're going to see that on the bottom right, we'll see those instances start to go down. And then as we move up to the top right here, we're going to have a log of the vessel. So that just came up. This is an init container, and what's it going to do is it's actually going to look at the cluster and determine what's happening. When it does, it's going to determine the workflow needs to be run. That is listed in the log here as lights out recovery. And then as you see here, these pods initializing, we're going to know what order they came in by how the log showed. So if you look here, we have different sequence numbers. We see 5, -1, -1. So we look here, we see the latest number is 5. So we have a different sequence number, and this instance represents the latest data in the cluster. Well, the other two instances, MariaDB 2 and 3, have different set of data. So we need to spawn MariaDB 1 first with the newest data, and we're going to bootstrap the cluster from there and have the remaining instances join. So you can see in the logs we do that, and if you follow it at the bottom, you'll see which one of them comes up first, and it will be MariaDB on MariaDB 1. So as demonstrated by this, the importance of a vessel, there are applications like this, a multi-master MariaDB setup, that are complex, that require additional help in cases where there are operations that need additional help, that can't just be a restart in order for the application to come back to full health. So there's a lot of danger in doing this if you don't have something to help you. So you can see here, as I demonstrated, how the vessel really makes the application seem more cloud native, because Kubernetes only needs to think this application is cloud native and interact with it exactly the same way. and the vessel will handle any of the in-between operations to really make it function and reach its cloud nativeness so that it can function in this environment very well. So that's all for the demonstration. There'll be more to follow as vessels develop further.